I should really say something about it because.
Like 4 minutes plays. It looked a little bit on the overview. That's kind of what you cover, developing your own tools for penetration.
Well, yeah, that's why I'm glad you brought this up. I should really talk about it because I'm sure a lot of people are trying to figure out what to do next semester. And now's a good time, or at the news area. So what's going to happen next semester is I'm going to have my most difficult classes, which are these two. 126 and 127 are the assembly language classes, basically. And these go in the detail of how exploits work and how computers work. The details of exactly how the memory is laid out and how memory corruption works. The malware analysis goes into how Windows works. And what you're learning about is the Windows API calls that underlie everything and how the Windows kernel works. And we will be looking in the kernel and seeing and corrupting the structure of the kernel with rootkits and such. And also, but most of it's in userland. And exploit development is primarily on Linux, although some of it's on Windows too. And this is buffer overflows, heap overflows, and string overflows. These are the fundamental binary attacks that underlie most exploits. And so these are, the programming is extremely simple. All the exploits consist of just a couple lines of Python sending a string. That programming is simple. What is not simple is understanding what happens at the other end. And that's where you have to learn to use a debugger and a binary debugger like GDB.
Okay. So
yeah.
Is it recommended to take these classes together?
A lot of people, it's up to you. You could, they're really quite unrelated. Exploit development is primarily looking at the raw assembly code in hexadecimal and seeing it byte by byte. And malware analysis is primarily the Windows API calls. So they really are quite different. And the malware analysis is probably a little bit less daunting to people who are worried about math and stuff because you get to use some familiar Windows tools in the environment, especially now. The most irritating tool in 126 is IDA Pro. And I'm planning to replace IDA Pro largely or completely with Ghidra, which is much, much easier to use. So 126 will be a little bit less scary this time. But well, these are my scariest classes that people freak out about, and also the ones that the sort of mathematically oriented people really value the most. Like my most technically advanced students joined the program entirely because of 127. They say, oh boy, now finally something. Because you like have degrees in computer science. Then 127 is learning how to do attacks with it, and it's like, exciting and exhilarating. Hey, I could do this. I could do evil with these techniques. It never occurred to me. This is what I got when I went to China at DEF CON last time. All these room full of developers, brilliant. Sailed right through this. They said, I never thought of using these skills for attack. This is great. And so these other ones are management classes, really. 152 and 152 is instant response at layer 7. Probably not installing tools, but using them. And this one's really management, CISM. So those are the less technical, and these other ones are the most technical for next semester. Anyway, it's a good question. Sure. And there's a ton of news, which I wanted to mention. Yeah, I'll talk about the schedule when we get to 10 minutes after and we're in the official time, because there's a lot of fun news I saw go by. This one is great. What's that? He was here and he left. His club just finished. He might be in his office. I'm not sure.
His office? Okay.
Yeah.
What's his office again?
On one floor up and over in this corner.
Okay.
Yeah, sure. Anyway, all right. This one's important. And this is pretty interesting. And it's not that exciting. This is very interesting. I think I want to start with that one. If I run out of time, this is the one I thought was most interesting. These guys claim to have a new solution to everything, the unhackable perfect plan, which is pretty interesting, actually. And what all this is there's address space layout randomization, where every time you reboot the machine, it rearranges everything in memory. That's what Windows 10 has, and Windows 7 has had, and everything's in Vista. And that stopped a whole class of attacks. And then there is Qs, which is Johanna Rutkowska's system to run a whole bunch of virtual machines and run like multiple browsers in different virtual machines so that your malware you get from Twitter can't affect your banking, because you do your banking on one machine. And what this is, it takes it to the next level. Every piece of software running in the machine randomly relocates every 50 milliseconds in memory. So the attacker can't find anything. And he said, if you do it at this rate of 20 times per second, then it does not slow down any of the operation very much. It only costs you like 1% in performance, but even the fastest exploit development process takes at least a few seconds, so there's no way you have enough time to perfect your attack before it moves. This is very much like WPA version 1. WPA version 1 took WEP, which was fantastically insecure, and just changed the key for every packet. So that even though the protocol is not safe, you don't have enough time to crack it before it goes on. And that turned out to be very effective. So this sounds pretty good. And I think this would end most of the stuff we do in 127. It would mean that all these attacks that rely upon injecting some kind of code and finding it and running it really wouldn't work, because you won't be able to keep up with this. But of course, I thought this comment was very perspicacious. I can get back to it. Yeah. Yeah, well, you know, this is a man that understands the point. If I can find the comment that led to this. Yeah, the point is, he says this will only prevent memory corruption, which is buffer overflows, dangling pointers and stuff. But of course, this is not going to do anything about SQL injection, because SQL injection is at layer 7, so your code is running and it injects unexpected commands into the code that's running. So just like hard disk encryption does not protect you from things like SQL injection because the server is running its decrypted data, this server is now shuffling the memory, but it's finding its way through the memory. So when I give it a command, which your server process executes, it will find it wherever it went in memory, and I won't have this problem. So he's got a good point. A whole bunch of attacks are at a different level. This mitigation won't stop them. But anyway, it will stop the kind of attacks that are in the exploit development class. And so it'll have some value. So this one is interesting and very much in target for this class. Filippo, I think this is one of the real cryptographers. Yeah, he's a cryptographer. I've heard of this guy before. Anyway, so this has apparently been known for a while. We talked about this a few chapters back. There's a random number generator and there's a pool of random entropy. But what if your computer suspends? Well, what happens is if your computer suspends, the entropy pool is gone. And when you wake up from being suspended, there's nothing in the entropy pool, so the random number generator returns 0. And this causes all kinds of weird problems. And this thread is him, who is, I think, well-known cryptographer, and probably quite right, explaining how he thinks this whole idea that you have a limited number of random numbers in the pool, and when the entropy pool is low, you can't get any more random, is all terrible, and they should just knock it off. And they shouldn't do this. And he said, this is why, because the code in the kernel says, if you don't have enough randomness in here, then you better just go back to something that returns a random number. And he's very much thinks this is whole wrong-headed, and this whole thing of having a limited entropy pool and worrying about it is wrong and leads to all these disasters. And other people are arguing the other side, and I'm not educated enough to know who's right. But it's a very interesting dispute. I put it in news link. This is, there are a lot of arguments about this. What is random, what is enough random, how to create random numbers is just a really hot topic. People have been arguing about it for years. Very smart people debate it, and I don't think we have any simple answer. And so, of course, the poor code developers that do something to write the kernel don't know what to do. They choose some religion in this and write code that does that, and then someone comes and tells you your concepts are wrong, and they don't know. So this is Apple. Microsoft is finally catching up with like Windows 95. I mean, Android is finally catching up with Windows 95. They're going to have over-the-air security updates for only certain key services. And also they haven't yet solved how to make all their distributors really get on board with it. But anyway, they're going to have hopefully more rapid updates for certain crucial parts of the operating system. So this might help. This is the huge problem with Android. Most people are using phones. They're like 2 years behind on their updates, which is ridiculous. And Google has been struggling about what to do about it and not really having a very effective solution. The Russian cyber spies, these guys sound like they'd be a lot of fun. These guys are straight out of a comic book. There's an APT group that uses the most exotic, outrageous attacks. They've been going around for years, and by keeping track of the time of day they work, they figured out that they're Russians, which is, of course, not perfect at all. But these guys, they made a special thing just to be an exchange server, just to be an email server to connect to others. Because one problem with email is email does not encrypt end-to-end. It encrypts with TLS point-to-point. So if I put a server in the middle, it'll encrypt and send me an email and I can get in. So that's pretty cute. It specifically targets Microsoft Exchange. And they have done so many bizarre things, which are straight out of science fiction. They hijacked telecommunication satellites to deliver malware. They hid malware inside Britney Spears' Instagram photos. They hijacked the infrastructure of ISPs. They've done all this outrageous stuff. So it sounds like they're the DARPA of Russia. Anyway, all right. And this is great. And I thought it was funny. The guy doing this, I know him. I, in fact, hired him years ago to write some stuff for me. He was a hacker in Florida, Scott Arsazowski. And he finally decided to fix WordPress security, which, by God, it really needs it. WordPress, like Android, is just a cesspool of insecurity. And one of the incredible things is the gigantic leap forward is, for the first time ever, WordPress is actually going to sign their updates. And I'm like, they weren't signed before this? I didn't realize. But apparently they never were signed. So now they're finally, the version coming out today is finally going to sign the updates. So I'm like, whoa, gee. Well, that is a giant leap forward, I guess, if you want to look at it that way. And by the way, of course, he's a smart guy, so they're actually using the latest, absolutely most perfect signing system, which is elliptic curve, with one of the curves we talked about last time. Not something wimpy like RSA. They're using a real modern signing library, which is fine. I'd be happy for any kind of signature. MD5 signature would make me feel better. But anyway, but while they're at it, they don't mess around. They use the best signature, so that's good to see. All right. Anyway, so we're up to the official time here. And let's talk about RSA, which I've added quite a lot that's not in the book, because your textbook author seems to me to be an anti-conspiracy theorist. He seems reluctant to regard things as being an evil conspiracy, and I am certainly not. I have the more common belief, which is an awful lot of cryptography is in fact an evil conspiracy. So I added that back in. Anyway, so all right. And this guy is very smart. So perhaps he's right that all this stuff I've read about the conspiracies is not true, but I don't think so. Anyway, we'll get there. So we'll talk about TLS. TLS has been the main security feature that we need to protect ourselves on the internet, and it has had a lot of problems. It sounds good in practice. There have been many things going wrong. So TLS 1.3 is the giant leap forward that is just happening right now. In fact, I was just reading about it. Android, the very latest version, one of the huge step forward is Android Q finally supports TLS 1.3. Only a few people do, and it is the giant leap forward, like when Microsoft went to XP Service Pack 2. And before that, their own developers didn't know what a buffer overflow was. They didn't know anything about security, and they finally stopped all development, made all their team read a book, learn some security, rewrite the whole thing from scratch. That's like what TLS 1.3 is. Yeah.
Does SSL have anything on TLS 1.2, or is TLS 1.2 still preferred to any SSL?
Yeah, every TLS, even 1.0, is far better than every SSL. Okay. SSL was the first generation from long ago when things were awful. Right. Okay. Yeah, that's a very important question. I'm glad you guys. There's never any reason to use SSL. Every version of SSL is considered hopelessly broken and deprecated by everybody. Anyway, so TLS is not actually in the transport layer. It's called transport layer security. That doesn't mean it lives in the transport layer. That means it's above the transport layer, and it protects data that came from the transport layer. It's in layer 5 or 6, but it's like most things. The OSI model doesn't really make any sense above layer 4. 5, 6, and 7 are all really blurred into one application, your email client, your browser, and there's no real clear distinction where things are up there. So, all right. But of course, because it's transport layer security, it doesn't really care what you're sending. It can send anything that TCP or UDP can send by adding a cryptographic layer on top of it, so it can be email, videos, anything, which is the idea. So it turned out, however, that the original one was sort of thrown together out whatever cryptographic tools they had in the 90s. That was SSL, and it had problems. And then they kept on bloating it by adding more and more features and more problems and more backward compatibility. So that's why you had all these attacks. Heartbleed came from the system of just adding new features all the time to TLS without testing them enough. So they added this heartbeat feature so you could have a keep alive packet, and they implemented it in a way that leaked out data. And Beast, Crime, and Poodle are all these Oracle attacks and ways that leak out attacks through weaknesses mostly in RC4 and so on. There's a whole series of attacks that occurred on it because it turned into a giant bloated suite with dozens of different systems and features, and that's how you make a mess. One of those is going to have a mistake. So 1.3 was the cleanup, where you start over again, throw away all the unnecessary features, make a simpler, much more secure, faster, better system. At least that's what they say. Of course, it's new, And usually in the world of technology, the new thing sounds great, and when you actually deploy it, something horrible is wrong with it. So I would expect there are probably going to be some patches. But so far, I don't think anybody's found anything wrong with TLS 1.3. But it's early days. All right, so the idea here is to make a secure channel. You want to have a encrypted, authenticated channel where one party can talk to another, like you can talk to Gmail and nobody else can see it. So you do this with trusted third parties to prevent man-in-the-middle attacks. That's your certificate authorities. So here's the requirements. You want it to be really fast, so it's not costing you more CPU than unencrypted channels, and that SSL does. There was a very common belief before about 2012 or 2013 that HTTPS was really expensive and you'd have to pay for a lot more servers, and then Google went to completely HTTPS. And they claimed at the end it only cost them 1% more CPU. So that was the turning point where they showed you can actually do it at scale, and more people are doing that. So you want it to work on every hardware, you want it to have some ability to extend, and you want it to be not tied to a particular application. Those are the basic ideas to make an all-purpose encryption protocol that people can use, and that's what we have, the TLS suite. So like I say, it's not, here's the OSI model, and it's not in the transport layer, it's in layer 5, 6, or 7, depending on how you look at it. And you can actually use TLS for UDP, then it's called DTLS, although I've never heard of anybody using that. That is an option. The only kind that is used for almost every normal application is the one that runs over TCP, which is called TLS itself. But I guess you could encrypt your UDP traffic from your security cameras or something, and that would probably be a good idea. So in 95, Netscape invented SSL. Netscape was the invented most of the system. They invented the magic cookie to have cookies in browsers. They invented a whole lot of the fundamental technologies of the web. SSL2 and SSL3 had outrageous security flaws because that was back in the bad old days when the people really didn't know much at all. The keys were too short. They didn't know about adding nonces. They had a lot of ridiculous mistakes made in the early days of encryption. TLS came out, it was much better than SSL, and it went through various versions. 1.1 was better than 1.0, but it contained a lot of algorithms, and some of them were weak. And 1.2 came out in 2008, but this had suffered from the most bloat. And it supports things that were unwise, like AES CBC, which you've attacked in this class, padding oracles. CBC, the cipher block chaining idea, suffered from padding oracles, and it inherited a lot of features and design choices from earlier versions. So 1.3 was the major overhaul and cleanup of the system. So there's two protocols. Once you have done first you do a handshake where you authenticate the party or both parties, and then you exchange a key. You decide on what cipher to use, and you exchange a key with Diffie-Hellman. And then you now have a shared secret. Now you have a key, and then you have a secure channel, and then you have record protocol where you just send records back and forth through that secure channel, encapsulating it. So this is the handshake. Cloudflare had a nice diagram of it. So first you do a TCP handshake with SYN, SYN-ACK, ACK. That just establishes that both servers are up and you are speaking, have to the right port and such. Now you have a private line. Well, you have a line to the other device, which is not encrypted. It is, however, true that the device can send packets to that device and they will be correctly routed and sorted so they don't get mixed with other packets. Yeah.
So this diagram shows two round trips in the TLS.
Yeah. Which is the 1.3. That's the one. Yeah, that's the old-fashioned system, I think, before 1.3. Right, 1.3 took it down to one round trip. Yeah, this is essentially the TLS 1.0 to 1.2 system. I think we're seeing here. So you do the TCP handshake, then you send a client hello. The client now says, okay, I want to talk TLS, and I support these 10 cryptography suites because I am like Internet Explorer version 6 or something. The server looks at the list and chooses one and says, okay, one of yours is good enough for me, so we will talk this one. So now that we've done that, we will exchange a certificate. I'll send you my key. You can send me your key. We will then both, if in the normal case, only the server prevents the certificate, the client now, it's not shown in the diagram, the client now checks with the certificate authority to see if the certificate is valid, or they should. But unfortunately, as we've seen in the Android class, a large number of apps do not, in fact, do that test. And if they don't, the server doesn't know. That is one, what you might regard as a logical flaw in the process. You can do this with a stupid client that doesn't actually check the CA, and that happens all the time. And nobody so far has found any solution to that. But anyway, so it is assumed to have happened over here, and then you're done. Now you have performed Diffie-Hellman, you have created a shared secret. You've used a shared secret to make a symmetric encryption key, and now you're going to be able to send data both ways with that shared encryption key. Now you have a secure channel between these two devices. And in practice, the way it's usually done, the server has a persistent key, which they use the same key for years and years, the same certificate for everybody, and the client has a temporary key generated in RAM of the browser for just this session and thrown away as soon as you close that browser tab. All right, so the client hello lists the available ciphers. The server hello picks one. You can see them in Wireshark very easily. I just went and connected to some website on Wireshark and picked it up in Wireshark. This is TLS 1.3. Here's 1.2, but in the 1.3, here it goes. And see, it sends all these cipher suites, 10 suites. So this stuff should be pretty familiar information by now. Let me zoom in for the people on the remote session. This should not be alphabet soup to you anymore. It's all TLS. This is AES 128 using Galois counter mode, SHA-256. Here's SHA-20 with Poly 1305, the latest cool stuff. Here's elliptic curve Diffie-Hellman. Here's Diffie-Hellman RSA, the old-fashioned stuff, and so on. These are all the modes supported by my browser, which is the latest version of Firefox running on Mac. It is your browser that chooses which protocols it supports. So if I were to put on a virtual machine and put Windows 95 and have IE3, it would have a whole different bunch of much weaker ciphers because that's all it had. And the server would have to decide whether it really wants to serve up data to things that are that old. And in fact, many tests have shown that most servers do support extremely old, weak protocols because they're just using the same certificate from long ago and nobody's really thought about it. But a modern browser will not offer anything that's too weak. So that's the server then replies. Let me shrink this back to the right size. Okay, this is the server hello. The server picks one and agrees to it. So this one here, it went to TLS SHA-20, which is the newest, like, fashionable one, presumably the most secure. So of course, when I say I can talk a lot of things, it chooses SHA-20 and Poly 1305 and SHA-256 as the latest and greatest. Let's use that. And now they exchange a key with that system, and that's it. Then we will now have a secure channel based on that. Yeah.
So one of the things that the NSA could do is if they know the cipher suite used, they can, and if they know that there's a exploit for it or a way around it, they can just read the handshake and you know that. Why? I mean, maybe this is a little foolish, but why not have like a handshake that's also encrypted so that even that data is not specifically leaked?
Well, I think it's just a chicken and the egg problem. There is no way to send encrypted data while doing the handshake because you haven't had any way to exchange a shared secret yet. So if there is no known way to do that. I mean, you could, well, that's the fundamental problem. I mean, you have to get started somehow. Yeah.
Well, and then also additionally, these encryption algorithms are designed so that regardless if you know them or not, theoretically, you shouldn't be able to break into it.
Well, that is, of course, the big issue, and that's where you get into conspiracy. She's suggesting that these have been poisoned by the NSA, which there is considerable evidence for in earlier versions. And if that were true, now you might wish there was some way. For example, if you had a VPN, then you have previously arranged a shared secret. And if they didn't get to steal the shared secret back when you negotiated that, then you'd have another layer of encryption. And if you were using a phone with a VPN, then in fact, an attacker like the NSA, even if they had a way to penetrate this, they would also have to penetrate your VPN. But you know, that's a fundamental problem. I mean, you have to somehow establish a shared secret at both ends.
I mean, why not start with like a public, you send your public keys, and
well,
then do RSA, and then through RSA you figure out the encryption protocol.
But that's what this is. The public key depends on the protocol you use. So first you have to choose a protocol, then it can send you a public key. That's exactly what this is. But there are many different versions of public key. And my browser might not support that type of cryptography. So that's what this is. This is saying, I want a public key, send me one of these 10 kinds of public key. And the server says, have you got one in that language? And that part can't be secret, I think. That's why I was sort of horrified when I started doing DNS monitoring. And I would look for DNS packets, and then I'd say, well, obviously I'll only see the port 53 DNS with the plain text name of the server on it. And I won't see other packets. And I always saw that the TLS handshake has got your name of the server in plain text. I was sort of horrified, but it has to. The certificate is sent in plain text. And the certificate has the name of the company. So if you don't want people knowing you're going to this company, you're hosed. Even TLS doesn't protect you. The only thing that'll protect you then is like a VPN. because there is no way to encrypt anything without starting in plain text.
Perhaps
Yeah.
you could just add another layer, like pick one of these 10 key exchanges, and then from here, let's choose an encryption algorithm that communication has been encrypted.
Well, you know, that there is an option. Opera, I think, did this. Opera built a VPN in every browser automatically. So you're always going to their servers, and everything's always got encryption from the start. At this point, I think VPNs are the only solution I know where you have encryption all the time from the very start. Other than that, you just have a fundamental chicken and the egg problem. If you're talking to a random server and you haven't had any time to prearrange anything, there is no way to start out encrypted. I don't know how there could be.
You agree ahead of time that you start off the handshake with the RSA, just sending an RSA public keys.
But that has to be sent in plain text.
Well, yeah,
And you have to have the name of the company to verify it, and that has to be in plain text because you haven't got an encrypted channel yet.
And it's like that's the whole reason why like enterprise Internet Explorer still exists, because some browsers just straight up can't support it, and some machines don't have that built into them. And like we're seeing here, some servers have limited options in terms of encryption.
But there is a general idea here, which you're bringing up, which is very valuable, which is this system assumes that you've all powered down and you don't know anything. You might be a version from 20 years ago, and we're going to start from zero and crank it up like a Model T. And there might be a way to start from a more technical, advanced position. And many people have proposed various protocols to do that, like encrypting your DNS and so on. And there's also flow routing. I mean, many things about the internet assume that you're in like 1980 and you're solving every problem from first principles, when in fact there are shortcuts we could skip to. And so, for example, if you use cell phone signals, it got a layer encryption, which were a different negotiation. Well, it's a very interesting problem. And I think this is the thing I like on the previous slide. If you want it to be all purpose and work on every device, then you have to start with this insecure stuff. But you might be able to sacrifice that and have a version. Like if I'm going to have an Android phone talking to a Google server, why do I have to go through this garbage? I had an opportunity there to establish a pre-shared secret, and I could have had one. And I think that's a very good point, and there may be ways to do that. And Chrome in particular keeps adding unapproved, non-standard security features that Google thinks up, like this, and they may become standards later. So you can totally do that. And you may be able to come up with a smarter way, because this is just the most general way that makes no assumptions. But that is not necessarily the best way to do it at all in the modern world. Anyway, so here's the book's diagram, more information. So it sends the client hello, telling me ciphers supported. Then it goes up here, the server generates a key pair, computes a shared secret, derives a key from it with the key derivation function, because the shared secret is not white. It doesn't have equal chance of 0 and 1 in every bit, and you want it to have that. So you take the shared secret, which although it's random, is not uniformly spread across the bits, and you run it through something, key derivation function, which is just something like 5,000 rounds of SHA-512 plus assault. And then you're ready to now send the certificate and the secret key here, and we can now work together. That's the 1.3 handshake process, one round trip, not two like that capture I showed, or that other diagram. So you have a certificate authority, which is not shown here. So once the certificate gets down there, the browser is supposed to go check with the certificate authority and walk the whole chain of trust up to make sure that this thing is really signed by a trusted person before accepting it. And that's the game. That is the trusted third party to prevent man-in-the-middle attacks. And every bit of this has been attacked vigorously and has its failures. So here's a certificate for Cloudflare, and it is issued by DigiCert, and the organization is here, and it comes with a fingerprint in SHA-256 and SHA-1, and that's what you get. And it also has a serial number, and these uniquely identified, and an expiration date, and you have to have the name of the company it applies to. And all that stuff has to come in plain text, because it comes before you have an encrypted channel. So then the certificate also claims the certificate chain. This is Cloudflare because DigiCert said so, and this intermediate CA, I trust them because this is the root CA, and that key is hard-coded in my browser. The public keys of the 100 trusted root CAs, approximately 100, are hard-coded in the browser by the browser designer, and your browser implicitly trusts all of them. And that is the fundamental way the system works. So that's the game. Here's the record protocol. You got a byte with the type of data and then other bits to specify how the block of data in the payload is sent. and just blocks of data are sent. You see them in Wireshark encrypted data going by. They now have zero padding, and I think at least TLS 1.3. I'm not sure about the earlier ones. There was a traffic analysis technique. Traffic analysis is a very powerful technique where you look at the size of the data packets. There was a paper I saw a few years ago that was good fun about this. If you use HTTPS and you load a page, if you load like Microsoft's homepage, it loads a block of HTML and then a little image and then a big image and then a little flash video. And so the pattern of sizes tells you what page you're on. If you're going to one of the top 1,000 pages, you can just fingerprint the pattern of byte sizes, of packet sizes that come. And so you can totally find out where people are going, even though you can't read the data. That's because it tries to compress things. So the modern one pads it to undo the compression, to waste bandwidth, and make it hard for traffic analysis. That's the modern technique. So here's the 1.3. You need three kinds of algorithms. You need an authenticated encryption. So you are sending data to a known party. You need a key derivation function to, like we talked about, to take the shared secret, which although random is not uniformly distributed through the right range of numbers, and you need a Diffie-Hellman function to establish that shared secret. And in principle, there are many choices for each of these. In fact, there are too many choices, including a lot of broken old ones, and you need to somehow agree on good choices for that. And so TLS 1.3 only supports 3 authenticated ciphers: AES in GLOAS counter mode we talked about before, in another counter mode, CC mode, and Cha-Cha 20, which is the newest, hottest, considered best one. Cha-Cha 20 or Poly 1305 is the new replacement, supposedly faster and even better than AES, although all these are considered very good. They all have secret keys of 128 or 256 bits. It doesn't let you have any shorter secret key. So all these are what is considered very strong and unbreakable these days. That's the point of it, of course. They removed all the old crap that you shouldn't be using anymore. Key derivation function is using HMAC, or SHA-256 or SHA-384. So those are nice, strong key derivation functions. Of course, if you're only making a 128-bit key, I don't really know why you bother making 256 or 384-bit hash function, because you're going to have to throw away half of it anyway, but that's what they do. And there are only 2 Diffie-Hellmans allowed: elliptic curve or the old traditional modulus prime numbers, nothing else. And the only the curves you're allowed to have are the NIST curves. I think there's 5 NIST curves. I think that should be 5, not 3, I forget. The NIST curves are there, of course, because you have to have the option of obeying the federal standards. And then the curve 255.19 or 448 that we talked about, which are the off-brand alternatives. And all those are considered very strong, although some people worry about some of those NIST curves. And then you've got traditional Diffie-Hellman. This is the weak spot, actually. You have traditional Diffie-Hellman, and you allow it to be as short as 2048. And although Diffie-Hellman originally was written for 512, and then people used 1024, became the standard on the web, now even 2048 is considered at risk. And we're all supposed to be going up to 4096. So some people say this is considered the weakest spot. This is actually only about 90 bits of security, and the rest of it's all 128. Of course, nobody's cracked 90 either, but it does seem kind of screwy when you have such a high standard to have a weak spot, and that's the weak spot. If you use 2048 for traditional Diffie-Hellman, then there is some, that is the weakest spot of a protocol that's really very strong in every other way, as far as anybody knows. So here's the improvements. They removed all these weak algorithms. We used to have lots of horrible stuff like RC4, MD5, SHA-1, you know, those things were awful and they're gone. So a lot of that is not there anymore. They got rid of the data compression. Data compression was intended to save a little bandwidth. This turned out to be far more dangerous because, of course, the degree of compression leaks out information about the plain text, and that's a side channel, and that's just begging for exploitation. And a bunch of the attacks used it, so they've just removed it. We'll just accept consuming more bandwidth for more security. They have downgrade protection, single script handshake, and session resumption. These are major features. The downgrade protection is really quite clever. So suppose you have this attack. I'm in the middle. Before you have the authenticated session, during the handshake, the client wants TLS 1.3. The person in the middle lowers that request to say, I only want TLS 1.1. The server gets a request for TLS 1.1 and hands it off. The client now uses TLS 1.1. This is a perfectly valid attack because it happens before the handshake is complete, when you don't have any encryption and you don't have any trusted third-party protection. This is a scary attack. And so TLS 1.3 mitigates this attack, and no earlier version does. And the way it does it, it has 8 bytes in the server hello packet. that the server sends back, which encode which version is in there. And those are cryptographically signed, so the man in the middle cannot alter them. So if the attacker does this, the message that gets back here will contain a flag to tell the client this is in fact TLS 1.1. So just like the verifying certificate, a smart client could detect this and warn you. The server has no way to know what's happening or to save you, but they give this client enough information to stop it if the client is smart. Now, in my opinion, that is a very weak spot, just like the certificate authority, because I happen to know how lousy the clients are, especially in Android apps and mobile apps. Giving the client an opportunity to fix it is a weak defense, but it is a defense. So if you have a good client, like say a modern version of Chrome, it's probably smart enough to detect this. If you have a crappy client like some commercial app, it's probably too stupid to use this security feature. But anyway, it is there, and eventually, presumably, the clients will be wise enough to use it. So that's good. All right, so in TLS 1.2, you send some data, get a response, you send more data, get a response. There's these two cycles, that's 2 round trips. Now it's combined into 1 round trip. I don't think that improves security, it just makes it faster, saves time, which is nice. And session resumption is another one. If you have already done the handshake and got a secure key, you can just resume the previous session and keep going. And makes me feel like this might be a risk. There were some weird renegotiation vulnerabilities in early versions of TLS where you could somehow renegotiate the key for some reason, even after you supposedly had a key, and there are ways to trick it into choosing a key you could find out or something. But this one, I haven't seen anyone suggest this is a vulnerability. And of course, it saves time, and it addresses the thing you were addressing. Once you got a shared session, why would you ever send any more plain text? Just use it. And TLS 1.3 does have that option. So here's session resumption with a different handshake. And you can resume it, and somehow I think you negotiate a new key using the previous shared secret. So that's pretty cool. And so this thing is really very strong. We're all using it. It's the #1 security feature on the internet. So you authenticate the server with a certificate and certificate authority. The client, in principle, could authenticate with a certificate as well. That is an option, but almost nobody ever bothers because it's too much bother to handle certificates in client side. So what they typically use is something like username and password for Gmail, or a secure cookie for websites once you've logged in. But you send some kind of information up to authenticate the client so they know who they're talking to. These things all have very good forward secrecy. TLS 1.3 has the best forward secrecy. 1.2 had a weaker kind of forward secrecy, so that even if an attacker is able to compromise the keys for one session, they cannot compromise old sessions with that data, which is what the NSA is primarily doing at their center in Utah, as far as anybody knows. So even if the attacker can steal all the data in RAM, they're only going to get the current session unless you have the old session keys in RAM. And this is one of my pet peeves. I've been complaining about this for a decade or more. Microsoft provided the solution in 2005, for crying out loud. I gave a talk at Hope about this. I demonstrated stealing passwords in RAM. I said, why are passwords sitting in RAM? Microsoft planned for this with this thing called the secure string. It's in your Visual Studio. You should put something like a password in a secure string. And the point of that is it will be deleted from RAM when you're not using it. Leaving secrets persistent in RAM is a chump move, like leaving persistent secrets on the hard disk. It's just developers that are being sloppy, but of course it happens. Anyway, so the CA is the heart of the whole system. You have to trust certificate authorities. This has turned out to be spectacularly unwise. Obviously, if you're in a country where the government can just demand things from companies, which I think the United States definitely falls into this category since the Patriot Act, then the government can just take over the CA and demand that you hand over the data, hand over the certificates, and they totally do. And they do it in China, they do it all over the place. And of course, if they are stupid, they actually get hacked by people, and this was Syria. The Syrian Electronic Army, I think it was the guy, hacked about 6 certificate authorities in 2011. And the most famous one was DigiNotar, dumped out their private key, made fake certificates for Google, and they were punished. It crushed the company completely. But a guy called the Komodo hacker, who claimed, I think, to be from Syria, hacked 6 other ones and only ever publicly exposed like 3 of them. And the others claim to still own them. And nobody ever knows which one they are. A lot of certificate authorities, in fact, are running flat networks with no firewall and no antivirus, no network segmentation. And I think DigiNotar, when they were exposed, they were not even putting serial numbers on their certificates. They did not even know how many had been generated or how many had been stolen. They hadn't been keeping track. And this is because in the early days, like in the early 90s, the only company doing this was RSA. They were the only certificate authority, and it was really hard to get a certificate. You had to show up in person, sign a form, get something notarized, have a business license, and then it got more and more popular, and they had third parties and lower level third parties until you had a whole bunch of people selling certificates, including discount cheap shops that are just run by some random idiot, and nobody's really auditing them for security or anything. So at some level, there are just complete idiots selling certificates with no reasonable security, and that's where we got here, to where even less than brilliant hackers can totally get in. And then, of course, there's these things that leaked out quite a bit in 2010 and later. These boxes are for sale for law enforcement officers to install on networks, to buy on the TLS traffic. And they just have a USB port, and in there you put your certificate authority root key, which you're supposed to get. And obviously they are readily available. And the open secret that I've heard, just like we all knew at this time that China was hacking everybody, even though it wasn't public, there was an open secret in the security community that all the certificate authorities would totally just sell you a root certificate to use if you bribed them. Because the major corporations need to have it. And this is why there's another side to this, which people get a real attitude about. They say, you call this insecure. It's much more secure to give me a root certificate because I need to open to man in the middle of the HTTPS session to see people are downloading viruses and leaking my company data out. You letting people have encrypted channels out of your company is kind of insane. You don't let people do that. Anyway, so there's arguments on both sides of it, but it's absolutely true that the certificate authorities do sell root certificates or intermediate certificates to other people. So when you look at that trust chain that Cloudflare had, or you trust this Cloudflare because the bigger Cloudflare vouched for it, if the bigger Cloudflare sells it to random third parties, then you really don't know. That really doesn't provide the security you might want to think it does. And so anyway, people have been arguing, screaming, and yelling at each other about this for a long time without a clear solution. But that certificate chain is not as beautiful as it should be. Here's GoGo In-Flight was seen giving fake certificates to everybody, and they were trying to explain that this was just for harmless surveillance to make sure you're not doing bad things or something. We're not really snooping on you. Well, this was a big attack at DEF CON. This was Applebaum and other people made this. Their RSA, until this time, which was 2008, they were using MD5 to sign the certificates, even though it was known to be broken. Now, but to be fair, so what they did here was they were able to create a rogue certificate that was connected to another certificate, but they had to buy a special certificate to make it happen. They were not able to like duplicate the Google certificate or duplicate the root certificate and sign everything. That would require making an MD5 collision that is so extreme that I can make a file that has an MD5 that matches a known published specific MD5. And that is not what they did. As we talked about, that kind of collision is still not possible even with MD5. The kind of collision that's possible is I can carefully craft two files that have the same MD5. But I can't just take an arbitrary file and match it. And that's what you'd really have to do to really get anywhere with this. This is why signatures based on MD5 are still not all that bad. But anyway, it did show a weakness, and it did humiliate RSA into moving up to SHA-1, and presumably they moved beyond SHA-1 now. Anyway, so suppose your client is totally hacked. Like you get malware on the client, it gets root on the client, it can see everything. And of course, it can take over the browser and see everything you're doing before it's encrypted. It can put on a rogue certificate, so you'll accept that. It can totally mess up your client. Heartbleed was outrageous. Heartbleed was for some ridiculous reason, they wanted to keep sessions alive, and for some reason, they made it possible to send data up and have it come back, which, by the way, is how pings work. Ping contains data. You can send data, and then the server echoes that data back to you. Now, I don't know why they did that. It seems like you might want like a session number so you can tell if the ping coming back is this one or the earlier one, but why you'd want to send like, blocks of data to the server and have it come back, I don't know, but for some reason they did that, and for some reason that could go up to 64 kilobytes of data in the Heartbleed, and it didn't get verified by the code on the server. So I could send it 1 byte and tell it was 64 kilobytes, and it would send me 64 kilobytes of reply, which was full of random unauthenticated RAM, uncleared RAM. So I would get 64 kilobytes of random RAM from the server and pump it out by every heartbeat. I could pump them out as fast as I want. I could just get random RAM samples, and it turned out that sometimes that RAM contained other people's private messages, other people's passwords, the server's master private key, and all the secrets would eventually leak off the server. So that was pretty outrageous, and it persisted for 2 years before anybody noticed, and there were no logs kept anywhere of this feature, so there was no way to look at the history and see what had happened. So it was a huge disaster. This was one of the major reasons why people started getting off their high horse and stopped saying Linux is more secure than Windows. This was the single disaster that wouldn't have hurt if you just paid for your software. Apple was immune, Microsoft was immune. It was only the open source people that got hurt by this, and they got hurt bad. And it totally put the lie to this long-standing belief that open source is secure because many eyes are looking at the code. The problem is you can post something ridiculous. There's another similar one that happened, which for some reason didn't upset people as much, was the failure of the entire Debian branch of Linux to use random numbers for 2 years. All the TLS keys were based on non-random numbers because when they compiled the Debian crypto library, some code wouldn't compile, so somebody commented out the line that seeded the random number generator. So all the random numbers were the same for like 2 years, and nobody noticed. And then it turned out that all the certificates generated on Debian systems for those 2 years were drawing from a small pool of random numbers, and you could totally break in all of them. And those were then used on hardware devices and Microsoft servers and everything, because the certificate might have been generated on Debian even when you're not using Debian. And that was another huge problem. So, you know, there's two models. One where you have the open source and everybody does it out of love for being a hobby, and you don't really know what gets done. And then there's the nasty corporate business model at Microsoft where some poor drone in Gilbert is being beaten on by the pointy-haired boss saying, you must audit this code, you must check these drivers, and maybe that's better because you know that certain kinds of work actually get done. Anyway, I think there's no simple answer which one is more secure. But people used to believe it was real simple. Microsoft is evil and open source is good. And I think they've gotten over that. Anyway, there's the SSL TLS test. This is good, clean fun. It will test for all kinds of security problems by just not only certificates. I did this a few times. I tested all the banks and colleges and everything to see how many of them are using badly out-of-date certificates. And a small number of them are, of course, using ridiculously out-of-date certificates. Let's Encrypt is another giant step forward from the EFF. TLS certificates used to cost like $500 a year, and a lot of people wouldn't use them because they're expensive. Let's Encrypt made them free for everybody, and they're going just fine. I think now something like 80% of all the certificates in the world are used by Let's Encrypt. So the next step, which has not happened yet, but I don't know why, is we might as well, everybody might start using client certificates because now they're free. But anyway, that hasn't happened yet, but certainly a lot of people jumped on Let's Encrypt. I and a bunch of other cynical, nasty people felt like they would probably just go broke, but that did not happen. I don't know how they're making money, but somehow they're still there. Been used for several years, got very popular. I've never heard anybody complain that they did anything wrong. They seems to be a huge success. I don't understand their business model, but somehow they're still up. So here's some other issues. STS is a security mechanism to warn you against protocol downgrade attacks. So the point of this is it tells your browser that you should only load this page over HTTPS and never over HTTP. So you can configure your server, and browsers that support this will not load the page over HTTP at all. That's a good one. Another issue is public key pinning, which I was surprised not to see in your book. This was a huge issue. This was strongly recommended and pushed out to everyone. In fact, it was pushed out so vigorously that something like 4% of the sites have it, and that number of sites that have it is still growing, even though a year ago Google deprecated and said quit doing it. But it takes, there's a delay in corporate movement. It takes years to educate people and get them implementing something, and then it takes years to stop once the industry is going. Public key pinning was the idea that since you don't trust HTTPS very much, and you don't trust the intermediate authorities, and you're worried that maybe they've been tricked into having the wrong certificate authority, you're going to put the public key on the client so it knows what it should be. So now it can do what you wanted to do, Caitlin. It can encrypt all the way. It knows what the key should be right from the start, which is fine. But the problem is, what happens when you move to a different hosting provider or change your certificate? How do you tell all those clients that you're using a different key now? It's not that you're doing an attack. That turns out to be a huge problem. And that's the fundamental problem, is key distribution. And this turned out to be so hard, expensive, and complicated and difficult to manage in practice that Google gave up on it and said, oh, we changed our mind. Don't do public key pinning. This turns out to just create a disaster. How do you even update your app? How do you update your server? Because now it's not going to accept anything except that key forever. Now what do you do if time passes and that key is no longer secure? Ultimately, this turned out to be opening a can of worms. So the modern solution is expect CT, certificate transparency. This is the new hotness, which is now recommended to replace public key pinning. So This will be a header you put on the server, and now the client expects to be able to go through a second channel. And the point of this is to deal with another huge scandal, which is OSCP. There is your certificate. Let me bring a real certificate up and point this out. So here's a samsclass.info. That's a good enough certificate. So I got a certificate here. And if I view the certificates, yeah, all right. Here's my certificate. I'm going to view the certificate. Okay. And someplace details. Okay. Here we are. Here's all the fields. Here it is, CRL distribution point. That's the certificate revocation list. So in the certificate, it tells me not only the name of the company and the name of the companies that vouched for it, it tells me where you should go to check to see if the certificate has been compromised and revoked. And so every certificate provider runs a server which hosts its certificate revocation list, and this has never worked right from the start. This has always been bogus. The problem is, for some reason, certificate authorities don't keep their servers fast enough. So it turns out a lot of them, the certificate revocation list server is either down or really slow, and so it takes a long time to query it. So what browsers have always done is they don't actually check the CRL. They make a token attempt to check the CRL, and if they don't get an answer within like 50 milliseconds, they just give up and let you see the page anyway and quit worrying about it, because the CRLs never really work. So that's pretty disturbing, because the CRLs contain certificates that you know got compromised. And so Chrome, to fix that, they had a non-standard solution. Chrome took all the CRLs and put it in the browser updates, because it turns out there aren't that many really revoked certificates. You can just store them locally. Then you don't have to ask anybody. But then they tried to replace this with a thing called OSCP, Online Certificate Status Protocol or something. And that didn't seem to work either. And this transparent thing is the latest attempt to do this, where somehow you have yet another trusted third party that you check to see if this trusted third party is not reliable anymore or something. And this is another thing that Moxie Marlinspike wanted to do, which I don't think worked, was to try to add the chain of trust back into it. He wanted to have some kind of reputation for certificate authorities, where you only trust this one, but trust that one less. He said this binary thing where we trust them all totally. Anyone not on the list, we don't trust them at all. That's not right. They should have reputations like Lyft drivers, where this one had been hacked 3 times, this one's been hacked 10 times. Or we have some kind of rating system going from people to people saying, how much do you trust them? And none of that has been implemented yet, although prototypes have been designed to these systems. But many people have tried to think some way. There's a fundamental problem here, and it affects DNS security too. You have to trust somebody. And whoever you trust will knife you in the back now and then. And then you'll say, I should never have trusted them. I should have trusted somebody else. Nobody has found any solution for this. And it's not a technical problem. It's a fundamental, logical problem of the universe. I mean,
who's working a little bit on that? There's quite a few like blockchains.
Oh yeah, Blockchange, of course. The big thing about Blockchange is supposedly you don't have to trust anybody. And then one of the big blockchains got hacked like a month ago, because it turned out that they had this list of bad guys, and a list of bad guys had to be synchronized. And if it wasn't, then you would trust the wrong person. Just the problem Blockchains were supposed to fix was not working. But you're right. That's the whole point of blockchains. Also have the latest hopeful, some way you can live without trusting anybody.
Like I've seen systems where it's like based on your continued good actions, you develop a level of authority, and then other users can trust you.
Yeah, that's reputation systems. And of course, then you have the problem. You can just generate a fake reputation. Pay a bunch of Mechanical Turk people to put good reviews up.
And just one day cash out on your.
Yep, or you can just sell out to an evil third party.
I think that's what they were going with staking as well.
Yeah, proof of stake.
You have a higher cost to be a bad actor.
That's the plan. That's why there was a paper that came out, I think I mentioned it earlier, about 2 months ago, where a guy did analysis of proof of work and showed it totally does not work. The actual financial cost of cheating is not large enough.
Yeah.
If you actually make more money by cheating on the blockchain than you would by playing the game by the rules.
If you can cheat efficiently,
then
it ends up being worth it.
Well, the whole point of the blockchain proof of work was supposedly you'd make more money by being honest, but his financial analysis anyway said that is not true. And you'd have to somehow have different protocols to make it work. Anyway, all right, so I got some cahoots about this stuff. Let me bring them up. That looks like them. All right. And I supposedly have a place to store the cahoots. Okay. 57, 19. Okay. Yeah, that's how we get to this place. Like there's some people that say, while you're trusting somebody, why don't you trust your own government, for Christ's sake? That's another way to go. You know? It's not a technical issue. It's a sort of religious value issue. Who do you trust? But there's no way getting out of trusting somebody. I don't think that's a kitten today.
It is not a kitten.
Looks like a turnip. It's a whale. Okay. All right. It's a whale, not a turnip. Okay. All right. Well, I'll give it a few seconds to see if there are any more. Apparently not. Okay. All right. So what version of SSL is recommended? Yep, none of them, all versions of SSL are long since broken and not to be used. Which message lists a bunch of ciphers? Okay, that's the client, starts it out with the client hello, saying what they can handle. Which is a fundamental issue of TLS2. It has this thing called flow control. The client determines how much data and how fast it comes and everything, because the general situation is the server is big and powerful and modern, and the client is a poor wimpy old cell phone, and the client has to say, I can only handle this, and the server has to give it only whatever the client can take. So which feature mitigates traffic analysis? Padding, of course. All right. What's the shortest secret key in TLS 1.3? Okay, 128, which is, of course, the minimum recommended these days. 100 bits is what you should have. 128 is good. Nothing shorter than that should really be used much anymore. All right, which of these is no longer recommended? Public key pinning. That was the issue. They recommended it. It sounded great. It turned out to be a nightmare in practice. And they said, well, never mind. All right. Whoa. That's a little bit better. An M. And dude. Are you dude? Okay, good. All right. Good. All right, so I got the winners. All right, so we're nearly at the end of the class. So I'll just say, I think this is one more class, and that's the end. This is 141. And let's see, here we are. Yep, there is class. We will have time to talk about quantum next time, and that's it. All right, and then there'll be a final exam week after that. So we're pretty much at the end. Oh, I should mention I updated a project where people are having a lot of trouble. Some people actually got project 17 to work, but I couldn't make it work, so I modified it. There were some, I was not able to get the very end to work. It wouldn't do an exchange. I think their blockchain is not working too well. Ripple just fell by 93%. So I think kind of it's sort of fallen apart. Anyway, yeah.
I mean, I know this is kind of like, doesn't make much of a difference, especially after last Saturday, but I got it to work after you modified it.
Yeah.
So
neat. Okay. That's good. Well, you know, two great things to work on Saturday. There are two projects I wrote that I couldn't get to work, and she made them work by following my instructions. So you got to go figure. I think my theory is in both cases, their servers, I don't know. I don't have a good clue, but I'm used to this blockchain stuff. That's why next version of this class, I'll probably get rid of the blockchain. So I think they will have ended by then. But all the blockchains seem to only work for about a year, and then they don't work anymore because they can't scale. And so anyway, I think we'll see if there's a blockchain really worth anything in a year, or if it's just a fad like the pet rock that went away. It's beginning to look like it's the pet rock, but there are some loyalists that are still convinced blockchain is going to save the world. We got to keep the faith. Yeah.
It's a fun visualization of cypher blockchain, seeing how that all works out and ways that you could
Yeah. I think the fundamental ideas behind Bitcoin are worth remembering, and maybe some version of like Interledger will come out and be used for supply chain management. But I think these public cryptocurrency type blockchains are going to just sort of fade out like a bad idea.
Trying to mesh 3 technologies into one overarching concept is a little.
We will see. There's a certain number of purists. Anyway, so I'm going to stop the share, and I'll go see if, oh wait, there's a chat message coming in. Even if the password is hashed like NTLM and stays in RAM, you can get it and crack it. Well, yes, that's right. Right. If you hash the password, you'd have to use a very secure system. Now, if you hashed it properly with like scrypt, then it would be very hard to crack. But yes, yeah, that's a good point. All right. Well, I'm going to stop the share and go upstairs to see if anybody wants help on anything.